I am pleased to introduce our first speaker of the fall quarter, Dr. Candace Tsai, and she is one of our newest faculty members in the department. She is an associate professor of environmental health and industrial hygiene here at UCLA. She's also a certified industrial hygienist. She has more than 18 years of post-educational experience in the field of industrial hygiene and engineering in both her academic and industrial career. She is a board member of Sustainable Nanotechnology Organization. She serves for the American Conference of Governmental Industrial Hygienists as a voting committee member for the Threshold Limit Values for Chemical Substances Committee. She received her Doctor of Science degree in Cleaner Production and Master of Science in Management Science degree, both from the University of Massachusetts at Lowell, and earned her Master's of Science in Chemical Engineering in Taiwan. So with that, I am pleased to turn things over to Dr. Tsai and take it away.
Hi, thank you, Miriam. Good afternoon, everyone. It's very nice to give this first presentation, this class. So today I'm going to talk about this project, which is relevant to a large collaboration among 3 different universities and with several collaborators. I just want to acknowledge them first. Here I list a team member, which involved my previous colleague at Colorado State University and my previous colleague at Purdue University. And it involved faculties in chemistry, physics, and myself in the environmental health sciences. So this is talking about the personal protective equipment, protective clothing, regarding the surface contamination and resuspension contributing to secondary exposure to nanoparticles. So this project, we target on looking into a specific lab coat material to look into the surface contamination and the possible resuspension of those engineered nanoparticles from the surface contamination contributing to the inhalation exposure. Because we found, based on my previous pilot study, we found there's a high risk of inhaling engineered nanoparticle released from those contaminated lab coat. We hypothesized that the inhalation exposure from manipulating those contaminated clothing will be very significant from all the nanoparticle and different type of fabric type testing. And we also proposed to do the surface treatment. And we hypothesized that the surface treatment can minimize the secondary exposure of nanoparticles. So we target to quantitatively evaluate the relevant engineered nanoparticle retention and the resuspension from the lab coat fabric. So we determine this level of exposure, utilize simulated motion on a mannequin wearing the lab coat, and then measure the potential exposure at the breathing zone to identify the severity of the exposure. And we characterize the material, the fabric, and the nanoparticle, and also we perform the surface treatment to see the differences before and after treatment. So we analyze the material we studied include 4 different type of fabric and 3 different type of engineered nanoparticles. So those 4 different type of fabrics are very commonly used fabric that people wear that in everywhere, in the hospital, in the industry. So they are Tyvek. Tyvek is a very popular material people use especially during pandemic. In those white, you can see those white lab coat. Those are the Tyvek lab coat, which is polyethylene. The polypropylene is a very common disposable type of lab coat material, popularly used, and you can easily get it. These 2 types are very popular that you can see it during the pandemic. And the other 2 types of lab coat made of cotton or the polyester cotton are those popular lab coat people wear in the chemistry lab. So in most of the chemistry lab, we wear this kind of lab coat, and you can wash it, reuse it, pretty durable. So we choose those 4 very popular type of lab coat for our study. The nanoparticles that we studied are, again, we choose the very popular nanoparticles, which aluminum oxide, which represent metal oxide nanoparticle. Carbon black represent a carbonaceous type of nanoparticle, and the carbon nanotube are the most recent new nanoparticle become the most popular one. So these three are being studied, and including in the project, we simulate the worker's motion to contaminate the lab code and to investigate the resuspension status from there. And we quantify, measure, and we characterize airborne particle and fabric material using electron microscope, including scanning and transmission electron microscope. And we also look into the surface property in terms of the hydrophilic, hydrophobic property, and then we specific treat the fabric with a material can change their hydrophilic, hydrophobic property. And then we further analyze the change in terms of the particle deposition and the resuspension. Okay, so just a few slides talk about the process and the equipment we use in this project. So we use for the exposure piece, the inhalation exposure part, we characterize, analyze airborne nanoparticle release from manipulating the lab code, simulating work exposure and the worker motion. We monitor using nanoscan SMPS and OPS. Both together can measure particle size from 10 nanometer to 10 micrometer. And we collect particles using multiple methods. We collect airborne particles using these two methods here are specifically designed for nanoparticles, which is, first one is my design, which has a patent already been filed. So this is called the Tsai diffusion sampler. I call that TDS. We use this to collect nanoparticle onto polycarbonate filter and then TM grid. Also use another sampler for nanoparticle called the TPS. It's a thermophoretic sampler. This one, we collect them side by side. This one collect particle onto the TM grid only. There's no filter being used. In addition to those, we also adopt NIOSH sampling method. So these are three different NIOSH analytical sampling method that we apply to collect particles and analyze them. So one of them being used, like 500 being used to collect and analyze aluminum oxide. 5040 being applied to collect carbonaceous type of nanoparticles, such as carbon black and multi-wall carbon nanotube. And we, in addition to that, we also use 7402 to analyze carbon nanotube, which is a fiber analytical method applied for asbestos, but which has been recently modified to analyze and collect carbon nanotube. Okay, so this is the procedure process that we simulate the work exposure to the engineered nanoparticle onto the lab code. So you can see the picture here that this is a mannequin, and this is the whole set is inside the class 100 clean room in my previous lab at CSU. This is a 6 feet wide film hood, and we have a double layer protection, this enclosure inside. The nanoparticle will be aerosolized on the left, and this is the lab code put on to the mannequin. So this mannequin right now is in my lab on the 7th floor. I think my students saw that mannequin. So this is a female mannequin, put the lab coat on, and there is a shaker on the bottom to simulate the worker's motion. So the worker simulate worker move during the work. So we simulate that gentle motion front and back. Aerosolization, release particles on the left and distribute to the lab coat. So this is the drawing of this enclosure on the left here. So we have two compartments here. So during the experiment, the compartment is open. So we aerosolize particle deposit onto the lab coat to contaminate the lab coat. And then we close the compartment on the right side and we purge the air. And we secure this one inside, and then we turn the sampling pump on with the real-time instrument to monitor the resuspension. So we keep this enclosed for a little bit, then we open it up and we start to shake the mannequin. So to simulate after the worker get the lab coat contaminated and then they walk away to another room and how much this particle can escape from the lab coat. So this is the process. So this is a procedure in terms of the time frame of doing this experiment. So we conduct two different sets of experiment. One is a short-term exposure and short-term release. The other one is long-term. So the difference is just the time here. The procedure is the same. So we do the pre-sampling, and then we measure the exposure, and then we hold for a little bit, and then measure the background before we do the release. So this is a purging time I mentioned about. We clean the air out after exposure, and then we start to shake the mannequin to measure the resuspension of nanoparticle from the lab coat. And then we collect the background sampling for the comparison. Okay, so in addition to those airborne particle characterization and inhalation measurement, we also characterize the material, the fabric. So the fabric, we characterize the mechanical property of the fabric, and these are the standard method, ASTM method, that we have the standard method to measure the fabric structure, thickness, the abrasion. We did abrasion test, which can give us, to tell us how durable the fabric is. And also we did the wettability test, which can show how breathable the fabric is. So we want the fabric to be breathable to humans that can feel more comfortable. So we did all these tests to characterize those fabric. So this is about the surface treatment. As I mentioned, we treat the fabric. We try to change the surface property of the fabric to see whether the surface treatment is able to minimize the secondary exposure contributed from the resuspension of nanoparticle. In other words, that the goal is if we can minimize exposure by either trapping nanoparticle onto the surface, so make a nanoparticle just very sticky on the surface, did not release, or the particle can be repelled right away. The particle did not deposit on your clothes. So the particle either get repelled or being get trapped on the surface very tightly. So these are our goal using the surface treatment. We try to change the surface property to achieve this goal, to see whether we can identify a specific surface treatment to a specific fabric and which work the best for a specific nanoparticle. So we have 3 different nanoparticles, 4 different fabrics. So at the end, we are going to prioritize to make a list of which one we suggest most for what type of nanoparticle in what kind of work environment. That's our final goal by the end of this project. So this is the setup that the treatment was conducted in this chamber, which is called a plasma treatment. So we treat the fabric using fluorocarbon and also water. So the fluorocarbon is to make the surface become more hydrophobic, and the water treatment is to make the surface become more hydrophilic. Okay, so we mount the fabric here, and then this located right over here. So it's a pretty small piece. It's probably like about 5 centimeter diameter size. So each time we coat the fabric about this size. Okay, so then let's move on to look at our data. This is just want to know this is an ongoing project. We haven't finished yet. We have another year to go on this project. So I'm presenting the data we have so far. So the current data, we have 3 different categories of data we have collected. The first category is regarding the actual exposure data from the mannequins contaminated lab coat. So we analyzed the real-time instrument data and come up with the concentration, size, distribution to analyze the level of contamination and the resuspension. The second category was the characterization of the material that we analyzed, such as the airborne particle collected on the filter on TM grid, and also the fabric, which has been contaminated with nanoparticles. We want to see the status of particle adhesion onto the fabric. And the third one is we specifically characterize the fabric surface interaction with nanoparticle about the surface interaction part. Okay, so this is the data regarding the contamination. So we aerosolize those three different nanoparticles, and we found the level of contamination from the aerosol concentration are different because that's the nature of the different type of nanoparticle. We found it's much easier to aerosolize aluminum oxide particles. And then the second one is carbon black. So carbon nanotube is much harder to aerosolize them into a very high concentration in the small size range. So you can see the graph show you the top layer here is a particle below 420 nanometer. So you can see a lot of particles are pretty small, around 100 nanometer, and has slightly different distribution among three different nanoparticles, and most of them are small. So for the concentration less than 10 micrometer, we found the carbon nanotube has very low concentration in this range. However, we conclude that the carbon nanotube actually has a lot of agglomerate. The agglomerate of carbon nanotube is actually beyond 10 micrometer. So we don't have the instrument above 10 micrometer, but we found that they are huge. Okay. So this is the data from the resuspension. So after the lab coat being contaminated, as I show you that the mannequin will be shaken so to simulate the motion. And we found the release from this process. This is the 30 minutes data. So we shake it for 30 minutes, and we found the aluminum oxide is expected because the high level of contamination. It does release the highest level versus comparing to carbon black and the carbon nanotube. And you can see the 4 different type of fabric, the Tyvek cotton, polyester cotton, and polypropylene. So we can see the cotton and polyester cotton come up with the highest level of the release of nanoparticle from the fabric. And also we found cotton and polyester cotton, they release not just nanoparticle, they also have some fiber will come up with cotton and polyester cotton. But the Tyvek and then polypropylene, we have much lower release from them. And they are pretty clean. We only see the nanoparticle. And again, like I mentioned that because a different level of contamination, the aluminum oxide get the highest. But it's very consistently that we observe cotton, polyester cotton, show up a very similar result throughout 3 different nanoparticles. They all release the highest. So what's the reason to make the nanoparticle release differently from different fabric? So this is regarding the adhesive force. That means the interaction between nanoparticle and the surface of the fabric. So there's 2 major force. Before we do the treatment, we only look at untreated fabric. There's 2 major forces that dominate the surface interaction of nanoparticle to the fabric that determine the adhesion ability of a particle onto the fabric, which is the van der Waals force and capillary force. So van der Waals force is very common for that. I believe everyone should be aware of that. So I don't further explain this. So capillary force is the one that are relevant to the water molecular. So you can see the picture here. So it's determined based on the moisture in the air and the water molecule attached to the nanoparticle. So it's under high humid environment. So the nanoparticle and the surface of fabric can come up with some water bridge because the water molecule in the air. That water bridge can form like a trapping bridge to adhere the nanoparticle onto the surface and also make a nanoparticle stick to each other if they are hydrophilic type of nanoparticle. Okay, so these are 2 major forces that are dominating the surface interaction for the untreated surface. Electrostatic is another force. We consider that, but electrostatic being considered to be very low in terms of the level of the force comparing to the van der Waals and the capillary force. But when we treat the surface, the electrostatic force become more important. So we can talk a little bit about that later. So this is the table to show you. We analyze the number of the fabric adhesion force. So the van der Waals force is also called the Hamaka force. So the table is showing you that we calculate the Hamaka force. So Hamaka force, the coefficient, the constant is H12 here, it can be calculated based on the constant of each individual material. Okay, so just jump into look at the data here. So when we look at this, and also you can see this Hamaka force is proportional to the fabric adhesive force. So by looking at the number here, so that means if the data is higher, that means it's supposed to have stronger adhesion to trap nanoparticle onto the surface. Okay, so we can see the polyester cotton is highest here. However, when we look at the result, it does not appear to be the polyester cotton trap a lot of nanoparticle. So why is that? So the capillary force, because the surface interaction was dominated by those two forces together, not just the van der Waals force, but also the capillary force. And for the cotton and polyester cotton, so remember the cotton fabric, you wear cotton t-shirt. So cotton absorbs the moisture, right? So in a raining day, you can feel the cotton shirt kind of wet, okay? Because the cotton absorbs the moisture. So the polyester cotton, the combination of that into the fabric, there's a 20% of cotton fiber into this polyester cotton fabric. This 20% of cotton play a very important role because it absorbs the moisture. So when the moisture gets absorbed, which means it take away the moisture inside in the air, so that means it reduce the water breach onto the surface. So that means it take away the capillary force. So it make the overall interaction of nanoparticle onto the surface of the fabric much lower. So it make a cotton and polyester cotton become much easier to release nanoparticle because the capillary force has been significantly reduced due to the moisture in the air. So this force is also dependent on the humidity. So let me just briefly summarize this session of the result. Is we found a very high level of airborne nanoparticle release out from the surface shaking of the lab coat, and especially aluminum oxide and carbon black showed a higher level of contamination and resuspension. And we found the distribution definitely are different because they are different nanoparticle, and we found CNT has a much larger agglomerate sizes. And then the surface interaction piece, that it really depends on the environmental conditions, such as humidity really play a big role because it affects the capillary force. And then that interact the total surface interaction come up with the van der Waals force and the capillary force together, because it absorbs the moisture onto the fabric. And if the fabric can absorb the moisture more, it can actually release particle more. And then just jump into the second section of our data is we characterize and measure the particle onto the fabric surface. So we have, how do we do that is you can see the mannequin with the lab coat, okay? But we have difficult time to measure the whole lab coat because it's too big. So we actually come up with a 5 swatch. So we cut lab coat, duplicate the same size, and we put it on 5 fabric swatches onto the lab coat. 2 at the front and 1 on the back, and 2 on the arms. Okay. So we weight each swap individually. So we weight before, after, and we see how much the weight increase after the shaking. So that means the weight increase will be the particle retained on the lab coat. So how much stay on the lab coat doesn't come out. And then we do the filter sampling with the flow rate 2 liters, so we can calculate mass concentration of this sampling on the filter. So here are several slides of result. So this is for the 30 minutes of the experiment. And we found, okay. So we found the cotton, you see the cotton fabric and the polyester cotton fabric. It come up with a high level of concentration, which is consistent to what we expect. And you can see the number here. And but when we analyze this, this is a mass data we measured before and after. So we look at the differences of lab coat mass change. And if we divided the differences, divided them to the original lab coat weight, just to see the delta M here, we divided that to the original lab coat weight. So this is to show up with like the percentile changes, but it's too small, so we showed out as a ppm. So we look at this data, then we found the polypropylene and the Tyvek is actually get very significantly much higher mass change per unit of lab coat weight comparing to the cotton and the polyester cotton. So why is that? It's because the surface actually come up with very similar amount of nanoparticle deposit onto the surface because we aerosolize particle under a very similar level of concentration. However, the polypropylene and Tyvek lab coat, they are very thin. They are very thin, very lightweight. And the cotton and polyester cotton are very heavy. So when we analyze per unit mass of the lab coat, we can see that the nanoparticles actually deposit a lot on the Tyvek and polypropylene particle, even though we didn't see that much coming out, but they are pretty much versus comparing to the unit mass of the lab coat. And it's consistent when we look at different nanoparticles. So this is data for carbon black. You can see they are consistent, and the same as carbon nanotube. You can see that. Okay, so it's pretty consistent about this data result. We found the number concentration pretty high on the on the cotton and polyester cotton release, but look at the mass, it's actually pretty similar, and actually per unit mass of lab coat is pretty high on the polypropylene Tyvek. Okay, so this is the 6-hour data. So remember the second set of experiment, we run this for the 6 hours, and we found the result is consistent to the 30 minutes experiment. We still see much higher concentration of the release out from cotton and polyester cotton, and it's pretty low on Tyvek and polypropylene. You can see the mass concentration, they are very different. And the mass concentration, you can see that very different on that. Okay, so this is aluminum oxide. So for carbon black and the carbon nanotube, we also analyze the carbon concentration. So so look at the data for the Tyvek and polypropylene, that the airborne concentration that we measure is much lower on these two type of fabric. However, the total carbon we measure that it's pretty high based on my experience of many different type of sampling onto the carbon black and carbon nanotube. You can see this is a 16 micron per cubic meter and 27 micron per cubic meter. Just to let you know, the current recommended exposure limit to carbon nanotube containing material, the exposure limit is 1 microgram per cubic meter. Okay, so let's look at this carbon nanotube. So I just said 1 micrometer per cubic meter, and you can see this data here. So this is like 18 times higher than the current recommended exposure limit from this experiment. So to just let you know, this experiment, when we contaminate the lab coat, we can barely see the contamination. So because they are so small. And because the mass is very low, but because they are small particles, we can just see some black dot, just a little bit. But when we shake it for 6 hours, we can see them come up with the concentration which the way exceed the current recommended exposure limit. Okay, so to summarize this, we found the Tyvek is still the best fabric for trapping aluminum oxide. Remember, I showed you the mass change per unit mass of fabric is very high. The high means the particle being trapped onto the fabric. They didn't get released out, and it's consistent to see those results from real-time particle monitoring that we found release from Tyvek is pretty low. Okay, so it comes up with very low resuspension of particle from the contaminated lab coat. Okay, so so the mass increase per unit fabric mass we found is pretty consistent from aluminum oxide and carbon black. But the carbon nanotube we found it's much lower, and the reason is because carbon nanotube has very low density and a very large agglomerate. So when we have such a large agglomerate, it gets fall off from the lab coat very quickly, easily. So we don't really get that stay on the lab coat that much. So that's the reason we don't get it. Okay. And also we measure the concentration in front of the mannequin and on the back of the mannequin. And we found at the front to come up with much higher concentration than on the back. Okay, so let's move on to some characterization of the data. So we use SEM-TM to analyze airborne sample and fabric and nanoparticles. So this is our images of 4 different fabric. Okay, so the first one, A, is polypropylene, and then the cotton, then cotton branded, and Tyvek. You can see the structure of the surface of the fabric. Okay, and then this is the images to show you that we have the individual small sample that we contaminate the surface, and then we shake it, and then we look at the same spot. This is a pretty challenging experiment that we did. We have to label very well, and then we can find the same spot and to analyze. I want to show you this. So like first one, you can see the top row is before shaking. The bottom row is after shaking. So shaking means that we simulate the motion to work away lab coat, and the particle, lab coat being shaken, and the particle can get released out. So we can see that, for example, this is carbon. This one is carbon black. Yeah, this is carbon black. So because my screen get covered on. Oh yeah, carbon black. So first is carbon black, and the second is carbon nanotube. And then the third column is aluminum oxide. So you can see that because this is the same spot analysis, you can see that we circle this location. Do you see it? Okay. So you can see that this particle here, no, actually this one is this. But you look at this, this one disappear. Okay, that's a shadow over here. Okay, but this one appear over here. So because we found those particles after shaking, they disappear. Okay, you can see it on the second one for the aluminum oxide. You can see there's a lot of shadow here. So those are the particles here. So we found many, regardless different size, small, big one, they all can be shaken